Well, good morning, good afternoon, or good night to you, my chemistry team. It's your chemistry coach coming at you. We are on a new journey today, something fresh you probably haven't seen in introductory chemistry or even in your first semester of general chemistry. And depending on the colleges, I've taught at other colleges as well, where we didn't cover this concept at all. So might be a little crazy. Once you get into it, it's kind of fun. We may or may not cover the whole chapter, but it's on complex ions. So in our particular textbook we're using for this semester, this will be chapter 24. But depending on what textbook you're using, what edition you're using, just look in the beginning table of contents and see what chapter that is. And remember, when you're doing lab, oxidants happen, baby. Yes, I have a whole closet full of these shirts that'll be coming at you. It's kind of like my pets. They just keep coming. All right. So what I'm going to do is just draw the formation of a complex ion, and then we'll break it down in parts and see how that overlaps with the equilibrium concept we're doing right now. So we've looked at equilibrium for water autoionization, weak acid ionization, weak base ionization, introduced slightly soluble solids, although we haven't really done the details of that chapter yet. But pretty easy concept where a solid dissolves to form two ions and forms an equilibrium. This one's a little bit different because all the other ones we've looked at, the neutral species are on the reactant side of the left side, and the ions are on the right-hand side, the product side. That's flip-flopped on this one. We're going to be forming complex ions from neutral species and ions. So you can have ions on both sides, but the topic of interest, the complex ion, is on the product side. So we're forming it. So the equilibrium constant is going to have a little sub F for formation of. So let's just take an example and we'll break it down. Let's say we have the zinc ion, which is always a +2, right? And there's no way you could predict at this point how many of this next species is going to react with, but I will show you how you'll be able to predict that simplistically on quizzes, exams, homeworks, and labs. So this can react with some ammonia. And it turns out it reacts with 4 of them. We'll see why in a second. And that can actually produce a crazy looking species where those ammonias dock in to some empty orbitals. Most people just kind of say empty d orbitals. And the coefficient becomes the subscript there. And these are neutral, agree? The ammonia is neutral. The zinc's got a +2 charge, so when we combine them all together, the neutral ammonias don't change the overall charge of the species, so it stays the charge of the zinc. So we're going to put this whole enchilada in brackets, and it has an overall 2+ charge. So the overall charge of this species called a complex ion. Why is it called a complex ion? Because it's complex. It's complicated looking. Right? That ain't your friendly neighborhood calcium +2 ion or aluminum +3 ion. That's some crazy stuff there. But the overall charge of this is just the charge of the metal ion plus the charges of all the species that are attached to it. And those are called, depending who you talk to, a ligand or a ligand. So let's identify these. So we're going to call this the metal ion. And that goes here. So this will be central, right? So over here we've got the central metal ion. And that's almost always going to be a cation. It could be neutral. Exceedingly rare for that to be an anion. That will not happen in this class. I'd have to say 99% of the time it's going to be a cation, right? But it could be neutral atom. This we call a ligand, or some people call it a ligand. I don't care. Potato. It doesn't matter. Ligand, it's irrelevant. So I had an office mate where we argued all the time. I'd be, hey, here's a ligand. They go, no, it's a ligand. No, it's a ligand. No, it's a ligand. It doesn't matter. All right. So just don't get upset about little things like that. If we look at this, remember the ammonia has, let's put it up here. That nitrogen has a lone pair on it, doesn't it? So what happens is that lone pair docks into an empty orbital on that central metal ion. So they come in and there's 4 of them. They go, yeah, you know, it's hitting me from every side. Knocking in there. There was a type of acid-base reaction we covered before. Remember we covered when we introduced acid and bases, we had the Arrhenius theory. So Arrhenius acids are anything that forms hydronium ion in solution. Arrhenius bases are anything that form hydroxide ion solution. Pretty limited. The Bronsted-Lowry concept, which is what we use, are the acids are proton donors, H plus donors, and bases are proton or H plus acceptors. That's the most useful for general chemistry. But when you get to biochemistry, organic chemistry, or complex ion formation, we have to use the third one, which is the Lewis theory. And if you remember Lewis theory, Lewis bases are lone electron pair or lone pair donors, and Lewis acids are lone pair acceptors, forming a coordinate covalent bond. So this is going to be, since it's giving both electrons, that's going to form a coordinate covalent bond. So this is, let me get blue here. This is my Lewis base. Ooh. And this is my Lewis acid. All right, this is my electron pair donor. This is my electron pair acceptor. This is Lewis base stuff. And that forms a coordinate, I'm not going to write it down, but that forms a coordinate covalent bond. And boy, it gets pretty crazy. So I'm going to show you real quick how we estimate how many of these it reacts with. And this right here, the number that it reacts with, the number of points of contact is called the coordination number right here. So this is a coordination number. So I'll do that right here. So coordination number, or we'll just go CN because I get tired of writing coordination number over and over and over. That's the number of points of contact that a lone pair attaches to that. So if 4 of these attach, that's going to have a coordination number of 4. So that's the number of points that a ligand lone pair attaches. All right, so in this scenario, this would be a coordination number of 4. And there's some exceptions to that. We'll talk about the details, but I just want to give you the basic idea of what's happening here. Now, how this folds into equilibrium, these can combine, right? The Lewis acid, Lewis base, or the ligand and the central metal. The ligand is the Lewis base. They combine to form this complex ion, but that complex ion could actually break back apart, right? So this is going to have a K value, and we call that the Kf value. So let me erase all this stuff here, and let's write the Kf, the equilibrium expression for this. All right, you ready? So I'm going to erase this real quick. You've got it on your video. You can pause it. That's easy enough to do. So let's write the K value. So that'll be the concentration of the product. That's aqueous, so we're going to include that. So we're going to have like double brackets. Kind of weird. So let's write that complex ion there. So, and that's raised to the power of 1, correct? This is aqueous, so we're going to include this. Let's put the concentration of the zinc plus 2 ion, and that has a coefficient of 1. And then the ammonia is also aqueous, so we're going to put the ligand in there. And there's 4 of them. So that raises to the power of 4, right? Nothing new there. That's just an equilibrium expression. And since we're forming the complex ion, right? We're forming a complex ion. You will see on the tables that this is Kf, the formation constant. And of course, just like we have Kas and Kbs and all those things, we have a Kf table. Woo, we can look it up. And so if we look that up from the Kf table, the Kf for this species, and we're going to learn how to, I am going to make you learn how to name these. Oh So we'll see that this will be called tetraamine zinc 2 ion. Tetraamine zinc 2 ion. We'll do naming in a totally separate video because it's cuckoo. But once you get used to the pattern of it, it's actually exceedingly logical. All right, so here is, and this is on my Canvas page, so here's our trusty dusty KF table. Looks just like the Ka and Kb tables. And you just look down and we look for zinc, which is probably down towards the end here. All right, so there's different ligands it can react with. So here's the zinc. Whoop, there it is. See the zinc right there with the 4 ammonias there? So that's a 4.1 times 10 to the, 4.1 times 10 to the 8th. One right there. Kf 4.1 times 10 to the 8th. So we can write that down. And these are huge. If you remember our Kas, our Kbs for our weak acids and bases, they range from like 10 to the minus 2 to 10 to the minus, 7, 8, 10, things like that. KSPs, you see, go all the way up to like 10 to the minus 40 in some cases. They're tiny, tiny. These are huge. K is way greater than 1, which means it's product dominant, way product dominant. And there's one extra factor I want to put on here when we do this. We're adding 4 ammonias. In reality, kind of like a polyprotic acid or base, it goes step by step. You add 1 ammonia molecule, then another, then another, then another. It gets successively harder and harder to form this. So there's a couple of requirements to form a complex ion. This will be a big hint, capital H hint, when you're doing labs going, how do I know if a complex ion is going to form? You need to have excess of this. This needs to be your limiting reactant. So you need to have an excess amount of that. That's usually assumed. And we have to have a pretty high concentration. None of this 0.1, 0.31 molar garbage. That ain't going to work. That's not going to work. We're going to have pretty high concentrations, pushing upwards of the 4, 5, 6 molar or higher. So here's the requirements, right? We need excess ligand. And we need a high ligand concentration. High ligand concentration. And my hint for you, right? Your professor is going to give you hints on exams. So if you see something like this, and I specifically say, hey, reacting with, 6 molar ammonia, whoa, red flag, big hint from the professor, probably gonna get a complex ion, all right? And the only other thing we need to do is, now I showed you how to look up the Kf values, and this is nowhere near complete. All right, this is just a few. This limits me to what I can give you on exams, unless I give you something weird and give you the Kf value. But you'll have that for exams, so I'll limit them to that. But there's a lot more complex ions you can form. How do we determine that number? All right, now that number is not always the coordination number, because there's different types of ligands that we're going to do in the next board. I'm going to pause that and talk about types of ligands. Some ligands only have one lone pair, like this ammonia, that can attach in one spot. Right? It's like a mosquito. Oh, got me right there. But there's other ligands that are bigger, and they might have 2 atoms on it, each with lone pairs. So they can come in and go, right? It's like a two-fanged vampire sucking in on me. So one ligand might actually suck up 2 coordination sites at the same time. There's some so big they can wrap around and attack at 6 locations at the same time, like you're getting stuck in a cage. They're crazy. We'll talk about what those are in the next, not the next video, but I'll pause it. So how do we look up this number right here? There is a table in your general chemistry notebook, but I have typed it up as well. It's on my website. It's a coordination thing for complexes. All right, so you can determine the coordination. You see the CN there? That stands for coordination number. Here's the metal centers, right? There's 2 parts to a complex ion, the central metal and the ligand, or ligand, no. Right, here's coordination number. And this is nowhere complete at all. But if we look at this one, do you see the ammonia? That was our ligand for this. What you do is you look for the zinc 2 ion. Do you see in the second row there? So, right, there's the zinc 2. If you look across for that ligand and that metal ion, it has a coordination number of 4. That means it's going to pick up 4 of them. That's how you determine that 4 number. So you just look for your ligand. La 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 la. Look for your metal. La 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 la. That tells you the coordination number. If it's not on there, oh crud! I should have given you a different one on the quiz. So let's look at different kinds of ligands and how they attach, and then we'll do nomenclature in a separate video. All right, one of the keys to doing complex ions, naming them, figuring out coordination numbers. We're going to do geometries as well. No, Vesper's coming back to haunt us. Ah! We have to know how many points of attachment a particular ligand does. Most ligands, we're talking well over 90% probably, only attach in one spot, right? Like a one-fanged vampire. We call those dentist. One tooth, it's a one-tooth vampire, or a one-fanged vampire, right? So things that have, like ammonia, had that lone pair here. All the halides, chloride, iodide, bromide, fluoride, they can all attach. Even though they have multiple lone pairs, it's only one atom. It can only attach at one point. To attach at more points, it has to have more than two atoms. Hydroxide has a lone pair here. The nitrite ion has a lone pair, and the oxygen. So what's going to be weird when we name things, we have to find out, is the nitrite ion attaching with a lone pair on the nitrogen or a lone pair on the oxygen? Oh, so you get these weird like nitro and nitrito and all these different ways of naming them depending on which atom attaches. And then water, of course, has a lone pair. And when we write like that zinc +2 ion with the AQ after it, it's actually got a bunch of waters. Remember that sphere? The lone pairs on the oxygens are docking in to that, so it's actually hydrated. It's a complex ion with waters bound to it. But we usually just leave that off because it gets too bulky and crazy. We just write AQ. Any ligand that attaches with has at least two atoms with lone pairs or more is polydentate, right? So something that had two atoms with lone pairs that attached at two spots would be bidentate. If it had three, it'd be tridentate or hexadentate, those kinds of things. Not many. These are about the only two we're going to run into as far as, bidentate. Do you see the oxalate ion here? I drew out the Lewis structure for it. Can you see all the oxygen atoms have lone pairs on them? But if we have, I'll do it in red here. But for example, let's take these lone pairs right there. See that one and that one? There's a metal ion right here. Chink! Oh, it's a two-fanged vampire. That's a bidentate. So that would have a coordination number. Just that one ligand sucks up two. That would have a coordination number of 2, right? So if something had two oxalate ions attached to it, that'd be 2 times 2 or 4. That would count as a coordination number of 4. Tricky. This species here, you see how long it is? The ethylene diamine. It's got 2 of those nitrogens on either sides of the carbons, ethylene diamine. It can attach here and here and wrap in and attack at 2 spots. Crazy. So, and there's tables of, if you look at the table here from your Gen Chem notes, there's a little superscript B that says, hey, if you see that, you'll see it's a bidentate ligand. So like the oxalate, you see that? Tells you it's bidentate. And then just know ethylene diamine and oxalate, you're good with the bidentates. Everything else will be monodentate for my class. All right, I'll try to simplify it. So it'll be easy to memorize. Just know those two. Everything else will be monodentate. And again, we're going to do naming in the next video. What I want to look at is how to break apart compounds that contain complex ions. So how do we know, like, what's the oxidation number on the metal ion, right? What's the coordination number? You got to know if it's a mono or bidentate ligand, all that kind of stuff. So I'll put some weird looking species up there and we'll just break them down in parts. All right, you guys ready to break some crazy complex stuff down? If you take a complex ion or a neutral complex species, usually it's an ion, and you make a compound, a neutral compound of it, sodium sulfate, it wouldn't be a complex ion in it, but the sulfate's a -2, the sodium's a +1, and you get a Na2SO4, right? Treat a complex ion exactly the same way. It just looks weird. And when you put them together, you get a coordination compound. That's a neutral species that contains a complex ion and a counter ion to create electrical balance, right? That's how you identify it. The reason they call them coordination compounds is because when the Lewis base, the ligand, comes in and attaches to the Lewis acid, the metal center, that's a coordinate covalent bond. So they're called coordination compounds. Hey, application of Lewis acid base theory. Let's take a look at this compound. What I want to look at is what's the coordination number on the central metal atom, what ligands are in there, what's the oxidation number, i.e. charge of the metal. That's what I'm after. So let's look at how we break this down, go back to kind of your first semester general chemistry, how you break things down. You see the sodium, right? And then you can see in brackets the complex ion. So would you agree we have 2 sodium cations? Everybody agree? And you all know sodium's +1, right? It's an alkali metal, always a +1, right? And since there's 2 of them, and there's only 1 of the complex ion, then we have 1 of the platinum Cl4 ion. But what's the charge on that complex ion? Well, you have 2 sodium ions for a total of +2, and you only have 1 of these. So it must be a -1 charge. I mean, a -2 charge. Duh, I'm looking at it with the -2, and I said -1. It's a -2 charge. Right? So one of these with a -2 cancels 2 of those with a +1, gives you a neutral species, charge balanced. Now we can break this. This is my complex ion. Let's take a look here. We've got, would everybody agree, 4 chloride ligands. And if you're not sure, you can always look on this table and you can just look and go, hey, there's the charge on it, because I'll be giving you this on test. So, but you should know the chloride's a -1. Based on this, we're going to look at geometry in the next board. What is the oxidation number on that platinum ion? Oh, let's break this down here. Well, there's only 1 platinum, and there's 4 of the chlorides, right? So 4 chlorides at -1 is a -4. So if you really break it down, you have 1 platinum, right? So let's break this down. I have 1 platinum. Let's call its oxidation number X. How many chlorides do we have? 4, each at a -1. That total is -2. So if you have trouble with this, review from first semester general chemistry oxidation numbers. All right, so if that's a -4, you move that over, it becomes a +2. So X must equal +2. So the platinum is +2. So I'd expect you to be able to do this on quizzes and exams, be able to break down a coordination compound into what are the complex ions, what's the other ion electrically balancing it, what are the ligands, how many, and let's get the coordination number. Chloride is a monodentate ligand. So what would be the coordination number on the platinum? It's picked up 4. So the coordination number would be 4. So the only thing missing on this is the geometry. So what I want you to do, I want you to pause your video, take a look at this one. It's a little more crazy. I want you to break it down into what's the complex ion, what's the counter ion, what's the charge on the complex ion, what are the different types of ligands, and are they monodentate or bidentate, what's the coordination number on that, and what's the charge or oxidation number on that cobalt. Give it a shot. All right, did you do it? I'll walk you through it. All right, you see the bracket, that's my complex ion. So this would be the nitrate anion. That's not my complex ion, that just gives it the countercharge. So if that's a -1, then this whole thing, since there's only 1 of them, right? I have a subscript of 1 here. That must be a +1. All right, let's take a look at this. So the CO NH3, oops, I forgot the 2 there. Boop. And then I put the NO2 in parentheses to make it more obvious. Got the chlorine, got the NO2. That must be a +1 to cancel the single -1 nitrate. So that's my complex ion there. Let's break that down. What kind of ligands do we have? We've got, I forgot it again. Keep forgetting that 2. So we've got 2 ammonia ligands. Those are neutral, and they are monodentate. We have one chloride ligand. So that has a -1 charge and is also monodentate. And we have one nitrite ligand, which is a -1. You can check this again. You can look on there, and you can see the charges of everything, right? And whether they're mono or bidentate. Since they're all monodentate, what would our coordination number be? So we have 1, 2, 3, 4. So we have a coordination number also of 4. You'll very commonly see that the coordination number is just double the charge on the metal. Not all the time. You know, maybe 70, 75% of the time, the coordination number would be twice the charge, but don't bet your life on it. All right, but everybody good? 1, 2, 3. I have 4 monodentate ligands. Pop, 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 attaches in 4 places. Now let's look at what's the oxidation number on that cobalt. Let's break it down. You ready? So we've got 1 cobalt. If you can see it in your head, you don't have to do all this. Let's call that X. Here's the ammonia. I've got 2 of those. But those are just 0, right? Those are neutral. I've got a chloride, 1 of those at -1. I've got 1 nitrite at -1. What must the total of the charge be? Equals +1. That's how you break it down algebraically. And again, review oxidation numbers if you don't remember. So that doesn't do anything. Right? That's a -1, -1. That's a total of -2. Move that over, and that's going to move the -2 over, and that will give me X equals +3. So cobalt has an oxidation number of 3. Right? So you got the +3. These are 0. Subtract 1, leaves you with a +1. Hey! All right. Let's do geometry real quick in this particular video. You ready for a little VSEPR review? If you don't remember this, go back to last semester, first semester general chemistry, and look up the valence shell electron pair repulsion theory and the different types of shapes, the tetrahedral, all that stuff. So let's just bang through this real quick. I'm not going to focus on it too much, but I would expect you to take a complex ion and be able to tell me the geometry of how those ligands are oriented around it. All right, real quick. If you have a coordination number of 2, say 2 monodentate ligands, they're going to attach on opposite sides, just like the VSEPR theory, right, to minimize those electron group repulsions. So they're going to have a 180-degree bond angle, and that is a linear shape. Remember. If you have 3, now that was a little different with VSEPR, so this is where this will be different. The dominant form is trigonal pyramid rather than trigonal planar. There's some trigonal planar. They're exceedingly rare. You're not going to see trigonal planar in my class. So pretty much if you see a coordination number 3, 3 monodentate ligands attaching in, we'll call that trigonal pyramid, where you got that metal ion and you've got that 3-sided pyramid, and the metal is at the top of that pyramid right there. If you have 4, 2 possibilities. The most common is tetrahedral. So always go tetrahedral unless otherwise. So tetrahedral again, you've got the central metal with 1 up, 1 down. You've got the wedge coming out at you, the dash going back. So the dash wedge structure, because we're in 3 dimensions, 109.5-degree bond angles, the good old tetrahedron. If you have nickel or cobalt triads, so if you look at your periodic table, okay, and look for nickel and cobalt. You see these? Although the triads were named before this last row down here. So nickel, palladium, platinum, cobalt, rhodium, and iridium. Those right there, if they have coordination numbers of 4, they typically form a square planar complex with 90-degree bond angles. It's planar. Not as common, but just watch out for those nickel and cobalt triads. And if you've got 6, 5 is not real common, so I'm going to skip 5. I didn't have space on my board. 6 would give you an octahedron or an octahedral geometry, right? Where you've got that square plane in the middle, 1 up and 1 down. So you'll see those a coordination number of 6. And now coordination number 6 could be 6 monodentates, 3 bidentate ligands, right? 2 bidentate ligands and 2 monodentates, whatever combination of coordination sites. So that's a brief intro into complex ions and coordination compounds. We'll do some nomenclature in the next video. Get ready, put your seatbelts on, it's crazy!